In the first part of this discussion, we explored the foundational idea that artificial intelligence is not a single machine or a single algorithm, but rather a broad engineering discipline focused on building systems that can perform tasks associated with human cognition. We examined how the field evolved from symbolic rule-based systems to machine learning approaches and eventually to modern neural network architectures capable of learning complex patterns from large datasets. In this second part of the discussion, we will look more deeply at how modern AI systems actually function internally, how they are trained, and what architectural components make them capable of performing sophisticated tasks. To understand the internal workings of AI systems, we must first recognize that at the lowest level they are mathematical functions. A trained AI model is essentially a complex mathematical structure that transforms input data into output predictions. The transformation is governed by parameters, which are numerical values learned during training. These parameters define how the system processes information. When we say that a model learns, what we mean is that these parameters are adjusted through a process that minimizes error on a given task. The model begins with randomly initialized parameters. It then processes training data and compares its predictions with the correct outputs. The difference between the predicted output and the correct output is measured using a function called the loss function. The loss function provides a numerical measure of how wrong the model's prediction is. Once the loss is calculated, an optimization algorithm adjusts the parameters of the model in a direction that reduces this error. One of the most widely used optimization methods is gradient descent. Gradient descent works by computing how sensitive the loss function is to changes in each parameter and then slightly adjusting the parameters in the direction that reduces the loss. This process is repeated many times across the dataset. Each iteration gradually improves the model's ability to produce correct predictions. Over time, the parameters converge to values that encode useful patterns from the training data. Neural networks, which form the backbone of most modern AI systems, consist of multiple layers of computational units. Each unit performs a simple mathematical operation. When combined across many layers and connections, these operations form a powerful system capable of approximating extremely complex functions. The first layer of a neural network receives the raw input data. This input might be a vector of numbers representing an image, a sequence of tokens representing text, or a set of numerical features representing measurements. Each neuron in the layer computes a weighted sum of its inputs and passes the result through a nonlinear activation function. The activation function introduces nonlinearity into the model, allowing it to represent complex relationships between inputs and outputs. The output of one layer becomes the input to the next layer. As information flows through the network, each layer transforms the representation of the data. Early layers often capture simple patterns, while deeper layers capture more abstract relationships. For example, in an image recognition network, early layers may detect edges and simple textures. Later layers may detect shapes or object parts. The final layers combine these features to recognize entire objects such as faces, animals, or vehicles. Training such networks requires a process called backpropagation. Backpropagation computes how each parameter in the network contributes to the final error. By propagating error signals backward through the layers, the algorithm determines how to adjust each weight to reduce the loss. Although the individual operations performed by neurons are simple, the combination of millions or billions of parameters allows neural networks to learn extremely complex mappings from input to output. Another critical component of AI systems is data representation. Raw data often contains noise, redundancy, and irrelevant information. Effective models must learn representations that capture the essential structure of the data while ignoring irrelevant variation. Deep neural networks excel at learning hierarchical representations. Instead of relying on manually engineered features, the network automatically learns useful features during training. This ability has been one of the key reasons for the success of deep learning in fields such as computer vision and natural language processing. Natural language processing systems provide an interesting example of how AI models represent information. Human language is inherently sequential and context-dependent. The meaning of a word often depends on the words that appear before and after it. Modern language models process text by breaking it into smaller units called tokens. Tokens may represent words, subwords, or characters depending on the tokenization method used. The model converts each token into a numerical vector called an embedding. These embeddings capture semantic relationships between tokens. For example, tokens representing related concepts often have similar embeddings. During training, the model learns to position these embeddings in a high-dimensional space where meaningful relationships are preserved. Once tokens are converted into embeddings, they can be processed by the neural architecture of the model. One of the most influential architectures used in modern language models is the transformer architecture. Transformers rely on a mechanism known as attention. Attention allows the model to dynamically focus on different parts of the input sequence when generating each token of the output. Instead of processing tokens strictly in sequence, the attention mechanism enables the model to consider relationships between all tokens simultaneously. The attention mechanism calculates how strongly each token should influence the representation of another token. By combining these relationships, the model builds a contextual representation of the entire sequence. This architecture allows transformers to capture long-range dependencies in text. For example, a pronoun appearing later in a sentence may refer to a noun mentioned earlier. Attention mechanisms help the model connect these relationships even when the tokens are separated by many words. Training large transformer models requires enormous computational resources. The process involves feeding massive datasets of text into the model and repeatedly adjusting parameters using gradient-based optimization. Training may take weeks or months on clusters of specialized hardware such as GPUs or tensor processing units. Once training is complete, the model can be used to generate text or respond to prompts. When generating text, the model begins with an initial sequence of tokens provided by the user. It then predicts the probability distribution for the next token. A token is selected according to this distribution and appended to the sequence. The process repeats, generating one token at a time. This process explains why language models sometimes appear to reason or explain ideas. In reality, the model is producing sequences of tokens that resemble patterns of reasoning present in the training data. The model does not perform symbolic reasoning in the traditional sense. Instead, it generates language patterns that often resemble reasoning because those patterns were common in the data used for training. Another important concept in AI systems is generalization. A model that performs well only on training data but fails on new data is not useful. Engineers therefore divide data into training sets and evaluation sets. The model learns from the training data but is evaluated on separate data that it has not seen before. Good generalization occurs when the model captures underlying patterns rather than memorizing specific examples. Achieving good generalization requires careful choices in model architecture, training procedures, and data preparation. Overfitting is a common challenge in machine learning. Overfitting occurs when a model learns the training data too precisely, including noise and irrelevant details. Such a model may achieve very low training error but perform poorly on new inputs. Techniques such as regularization, dropout, and data augmentation are used to reduce overfitting. Another important concept is inference. Training is the phase in which the model learns parameters from data. Inference is the phase in which the trained model processes new inputs and produces predictions. In many real-world systems, inference must be performed quickly and efficiently, sometimes in real time. Deploying AI systems therefore involves engineering considerations beyond model accuracy. Engineers must consider computational efficiency, memory usage, latency, and system reliability. In addition to technical considerations, artificial intelligence systems raise important questions about reliability, fairness, and transparency. Because AI models learn patterns from data, they may inherit biases present in that data. Detecting and mitigating such biases is an active area of research and engineering. Interpretability is another important issue. Many modern AI models are extremely complex, making it difficult to understand exactly why they produce specific outputs. Researchers are developing techniques that help explain model behavior, such as identifying which input features influenced a decision. The field of artificial intelligence continues to evolve rapidly. New architectures, training methods, and applications appear every year. However, despite the rapid pace of innovation, the core principles remain consistent. Artificial intelligence systems operate by learning patterns from data. These patterns are encoded in the parameters of mathematical models. Training algorithms adjust those parameters to minimize error. Neural network architectures transform inputs through multiple layers of computation, creating increasingly abstract representations of data. When we step back and consider the broader picture, artificial intelligence can be understood as a method for building adaptive computational systems. These systems do not rely solely on predetermined instructions. Instead, they learn from experience in the form of data. This capability allows AI systems to operate in environments that are too complex for traditional rule-based programming. Whether recognizing speech, translating languages, detecting anomalies in financial transactions, or assisting scientific research, AI systems extend the range of problems computers can address. However, it is important to maintain a clear perspective. Artificial intelligence does not replicate the full richness of human cognition. It does not possess self-awareness, emotions, or independent intentions. It is a powerful set of tools built on mathematics, data, and computation. Understanding what AI is therefore requires understanding both its capabilities and its limitations. It is neither magical nor trivial. It is the product of decades of research in computer science, statistics, neuroscience, and engineering. As engineers and technologists continue to develop these systems, the focus increasingly shifts from simply building powerful models to integrating them responsibly into real-world environments. This involves designing systems that are reliable, transparent, and aligned with human goals. Artificial intelligence represents one of the most significant technological developments of our time. Yet at its core, it remains a computational method for transforming data into decisions and predictions. By understanding the architecture and working principles behind these systems, we can move beyond myths and misconceptions and engage with AI as engineers, researchers, and informed practitioners.
If you find this video exciting, please like, subscribe, and turn on notifications. See you in the next AI for Beginners educational video.